Hello, friends. Today we will have a new topic introduced, which is called as root locus design or root locus construction. The previous topic of difficulty 2 in Rahutare, we will come back again. A small portion of which is left to be discussed with you. I will see that we take it up again shortly. But today, let us keep before us techniques which are involved in constructing a root locus. It's something very important. And though this technique was developed in 1960s, but sorry, it was developed around World War II in 1940s. It has remained immensely popular and significant in design of control systems, and present day systems also employ use of root locus technique in analyzing the model and system stability. So we will look into this, such called as root locus design or techniques for constructing a root locus. Now, this is actually a graphical technique that allows us to obtain all possible positions of the roots of the characteristic equation by varying one of the system parameters. Now, we see before us a unity feedback closed loop system, right? So what will be the characteristic equation for this? Yes, the characteristic equation of this will be written as, but before that, let us write down the transfer function for this overall transfer function. Overall transfer function for this unity feedback closed loop system will be G of S upon 1 plus GS, right? I will attach HS also. Anyway, HS is what? Unity here, unity feedback control system. H of S here is what? Unity. So for me, normal representation of this closed loop transfer function is ratio of two polynomials P of S by Q of S. And the characteristic equation that I was talking will be obtained by putting denominator polynomial equal to 0, right? So the characteristic equation here will become something like this: 1 plus GS HS equal to 0. So this becomes our the characteristic equation. Now, if I have one of the parameters which normally is system gain k, right? So how I can bring that k also here? So let me say this is something like k into, right? Let me get out k here, from GSHS. So let there be controller gain k, right? Okay. So here there will be something like then kgs, and here it will be what? K, right? So it will be 1 plus k GSHS equal to 0, right? If I am having a controller k also, right here, just to allow us to understand which parameter we are going to vary. Now, in this case, we know there will be the solution of this characteristic equation gives us what? The roots, which are also called as what? Poles, or also called as what? Known as eigenvalues, right? Eigenvalues. Now, as the k changes in equation, we see these roots of the characteristic equation will also change, right? Now, we have a graphical technique which we will call as root locus method, that allows us to obtain all possible values of these roots, right? That will be generated on varying, let us say, the open loop gain k, right, or controller gain k to its complete range. Normally, we vary it from 0 to infinity, right, over its complete range. Right now, the significance of this can be understood, of this method root locus can be understood when we will see that these roots, right, roots of characteristic equation are obtained only from information on open loop transfer function GSHS. This is the no, power of the technique, beauty of the technique that Evans has developed, and which we call as root locus technique. This technique allows us to obtain the roots of no, characteristic equation of the closed loop system, uh, inspecting knowing only the open loop transfer function GSHS. Right? So this information will be enough for us to know the no, all possible uh, values to the roots of the characteristic equation. So how it is done, we will see, but this is what basically root locus technique is. That tells us the entire loci of roots that would be generated, right, by varying one of the system parameter by knowing only the open loop transfer function. This you should underline, right? The knowledge of alone open loop transfer function is enough to obtain the entire loci, right? Set of possible values of roots of the characteristic equation. To understand it more, let us look at one simple example here. Let me erase this. So yeah, let us see for a unity feedback control system, if we have a second order open loop transfer function g of s given by this. In this case, what will be the no root locus, right? In simple way, without no uh, getting started with the rules and techniques of generating a root locus. Let us understand in simple way for a second order system. Root locus technique allows us to obtain that locus for any higher order system, which otherwise would have been very difficult. So we first see a simple second order system. Later on, we start with the root locus techniques. So here, when we have a second order control system, what will be its characteristic equation? Characteristic equation will be 1 plus GS HS equal to 0, right? For the closed loop system. And when we put the value of GS and HS, GS is K upon S into S plus A. Yeah. So this is S upon S plus A, right? HS is what? 1. And this equal to 0. Or characteristic equation becomes S square plus AS plus K equal to what? 0. Right, friends? That is what we see. Now, what will be the, that is what no I have stated here, S square plus AS plus K equal to 0 is the characteristic equation for this given unity feedback closed loop system, of which G of S is given by this. Sorry. So what will be the roots of this? Since it's a second order system, it will have two roots, S1 and S2. and we use that quadratic equation formula, find out root. It will be minus b, here it is a, plus minus under root of b square, it will become a square, minus 4ac. A is 1, c is k. 4ac, 4k, right? Divided by what? 2a. A is 1 here, right? In standard notation. So by 2. So this will be minus a by 2 plus minus. If I take 2 inside the radical, it will become 4, right? So it will be a by 2 whole square and minus k, right? That is what we have no, obtained here, written down here. So these are the two possible roots of the characteristic equation. Now, this you can see depend on the value of open loop gain k. Value of what? Gain k. As k varies, the uh, position, right? Values of the roots also will change. Let us see how it dances along the variation in gain k. So if we have a complex plane here, you have vertical axis as standard j imaginary frequency axis, and this is the real frequency axis, right? Sigma. So when I in beginning, let me write here somewhere, not getting space here. When I write here k equal to 0, right? Starting for k equal to 0, the two roots s1 and s2, what they will be? Yes, it will be minus a by 2 plus minus a by 2, right? Then in that case, what it will be? For plus, it will be 0, and for minus, it will be minus a. So 0 and minus a become what? The two solutions for the characteristic equation. So I write down here one pole, the roots are nothing but pole, right? One pole is at 0, another pole is at minus a, another pole is at what? Minus a. And these are the values when k is equal to 0, right? These are the values of the poles when k is equal to what? 0. Now I increase k and make k equal to a square by 4, right? Or a by 2 whole square. In that case, what will be the two roots, s1 and s2? We see here when k is equal to a square by 4, the two roots are repeating themselves at what? Minus a by 2, because square root will be 0, right? These two terms are same under the square root. So radical becomes 0 and two roots become no at fall at minus a by 2. They are occurring at same place. So somewhere here is, let us say, minus a by 2. So we have multiple roots at minus a by 2, right? When k is equal to a square by 4. So as k has increased, the two roots have moved from their earlier position, which they were found to be when k was 0, now to what? Somewhere in between, right? Middle of that at minus a by 2 when k has increased from 0 to a square by 4, right? Now, as I increase k further and allow it to become what? A large value, let us say infinity, what will happen? Yes, one root s1 will be what? Minus a by 2, let us say plus infinity. So anything subtracted from infinity will be infinity. So one root moves towards infinity and another root minus a by 2 minus infinity, right? Because radical has plus minus. So when I am considering minus sign, it will be minus infinity. So minus infinity summed up with any quantity will be minus infinity. So another root is moving towards minus infinity. So one root moves towards plus infinity, right? It should be a straight line, plus infinity. And another root moves towards what? Minus infinity, right? This is moving towards minus infinity. And this root is moving towards what? Plus infinity. So in this way, you can see that the the no possible values of roots of the characteristic equation, they shift, they move, right, from point to point in the complex plane, corresponding to the changes in the value of open loop gain k. Now this locus that we get, right, you can darken this region on the real axis, which is part of root locus. This locus that we get, right, is called as root locus. And root locus, you can see it started with what, k equal to 0, and it is no progressing for no higher values of k, which we are saying is approaching to what, infinity. So I can say here now in no in control system no parlance that we have uh, we have two branches of root locus here, right? Each branch starts at what? Yes, open loop pole. Where what are the open loop poles? This is open loop system, right? The root locus is for closed loop system, but that would be related eventually by events with what closed loop system later on we will see. So the two branches start at what, open loop poles. You can see here the open loop poles will be what, when you plot pole zero mapping, one pole will be at 0, another pole will be at -a. So root locus has two branches. Each branch originates at an open loop pole with k equal to infinity, right? And here the two branches later on move towards what, infinity, in opposite direction as k tends to what, infinity, right? So this is what is called as root locus, right? The loci of roots obtained for no varying a given quantity, in this case is open loop gain k, along its entire range for from 0 to infinity. Now here it was easy for us to obtain this root locus, right? uh, Given it was a second order system, but when we have higher order systems, right, uh, factorizing a higher order system is not easy, and then no obtaining root locus will be more cumbersome and difficult. For that, we have a technique given by Evans, which is called as root locus technique. Let us see that, right, friends? So, but the points that we can carry from here, from this discussion, is something like this. One point we see is what, the root locus, right, has branches, right? The number of branches are equal to open loop poles, right? And second point can be each branch, right? Each branch originates, right? Originates or uh, starts at what? Open loop pole. Each branch starts at open loop pole, right? Where when k is equal to 0. And third, the branches are no terminating, right, at infinity, right? Right? Where do this two branch go and stop? They go to infinity, right? As k tends to infinity, right? We see here the values of roots will also be what, infinity. So it approaches infinity with k equal to what, infinity. So these are some of the things which we can carry forward from discussion of this simple second order control system in developing the root locus that would be valid for any higher order control system. So here we formally introduce the definition of root locus, right? It's a graphical method of plotting the locus of roots of characteristic equation in S-plane as a given system parameter is varied over the complete range of values from 0 to infinity, right? Or the root correspond now what is that further we can know do with this root locus? For a given root locus, right? Like in the case which we just saw before, our root locus was something like this, right? So it originated at 0 and minus a, and at minus a by 2, uh, at minus a by 2, it 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 was what, breaking away from real axis, right? The root locus started on this real axis here at 0 and minus a, the two branches. The two branches met each other at minus a by 2, and later they departed real axis. They left real axis, and roots later on became complex. So from 0 to right, when k was, right, I'm writing this for k, when k was 0 to what, a square by 4, roots were real, right? Roots were real. And for k greater than a square by 4, roots, they became what, complex, right? And that is how the root locus progressed, developed further. Now, for a given point, right? For a given value of k, for a given value of k, I can find out the corresponding roots in the roots from the root locus. One point is what? For a root locus that we have developed, one point is for a given value of k, right? It can be some value of k, 50, 100, 20, anything. I can find out what will be the corresponding roots, right? What will be the corresponding roots with help of the developed root locus. How we will see that, right? But this is what we can know further determine once we have obtained a root locus. So for a particular value of k, the corresponding roots of the characteristic equation could be obtained. And second is we can go vice versa. For particular roots, right? We can know what will be the gain k, right? So this also we can find out. Now, we need to know this because if by varying gain k, if roots are becoming unstable, or what I mean is system is becoming unstable, then that I would be coming to know from the root locus. Here in this case, I have for all values of gain k, roots are what, no, always lying in the left half, right? You can see that root locus always, for any value of gain k, you will find no roots are only on the no left half. They remain only along this vertical line, right? As k goes on increasing, the corresponding two roots, right, they only keep on shifting along this vertical line, right? So for all values of gain k, here system will remain what, stable. We know if roots enter in the right half of the S-plane, that indicates a unstable system, right? Response will be what, unstable. So this is something very important what we know analyze with help of a obtained root locus about the range of possible values of k that allows us to know keep system stable. And remember, here when we talk roots, we talk of what, roots of the closed loop system, closed loop poles, right? And we will see that, right, friends? So in some cases, no, you will see that you have root locus which even move towards no right half, like no, we have here something like this, we will see soon, right? So when you have three uh, poles, uh, open loop poles, you may see that the corresponding root locus, right, these two branches, right, of root locus, they start progressing towards each other with increase in gain k. Each starts at k equal to 0. So here the root locus will develop something like this. The branch that is generating at this open loop pole will move in this direction. Why? We will see. Whereas these two branches that generate at these two poles, they move towards each other. And we see that as k increases, the branches, they break from real axis, and they get this direction. They get this kind of direction. So as k increases, the root locus moves into the right half of the S-plane, right? The root locus intersects the imaginary axis, and later on, for further higher values of k, it eventually enters into the right half, that thereby indicating that in this case which I am talking, system is not stable for all values of gain k. You have to keep k in some restricted value, right? It has to be less than equal to some constant k1, so that the root of the closed loop system remains in the left half of the S-plane only, right? So as long as the real part of root is negative, the root locus remains in what? Left half. And once the real part of roots become positive, the root locus have entered into what? The right half of the S-plane. So we will see how to find out this, something interesting. But you see, this is what I mean, right? When we say that the root locus allows us to find out the value of gain k, right, for a particular roots. So we can find out when roots are imaginary what is gain k, and as long as we keep this gain k less than the value for which roots become imaginary, system remains stable, and for any increase in k greater than this would lead system to be no, unstable. So we will see these 2 points. Now, before that, let us understand two important criteria which Evans has used in developing his graphical technique, right? A great contribution by Evans in developing this method called as root locus, that allows to know the stability and system analysis quite easily with developing a simple graph. Now, the criteria that we will have is obtained again from the characteristic equation, since this talks of roots of the characteristic equation. So we know a characteristic equation of a closed loop system will always be given by this particular equation, right? 1 plus GSHS equal to 0. Now, doing simple realignment, we get GSHS equal to -1 from this equation, right? And when I say GSHS is equal to -1, we know they are complex functions, right? Since S is a complex quantity. So we will get two conditions. One, when magnitude of GSHS is equal to 1, if I take mod absolute value of GSHS for this equation, the absolute value of GSHS will be equal to 1, which is called as magnitude criteria. And the angle contributed by GSHS, right, should be what? Since it is -1, so angle contribution should be what? A odd multiple of what? 180 degrees, right? Because we know cos of pi is what? -1. Cos of 3 pi is what? -1, right? And this complex quantity is becoming -1. So angle contributed by GSHS, right, has to fulfill this criteria, that it should be a odd multiple. 2q plus 1 will always give you a odd multiple of what? 180 degrees. Now, these two criteria, the magnitude criteria and angle criteria, tells us that for any point to lie on root locus, right? Here, which points in S-plane lie on root locus? This point, or this point, right? Or the points that are falling on this progressing root locus, right? All these points, they lie here on what? Root locus. Now for this point to lie on root locus, it has to satisfy two conditions. One, the magnitude of GSHS at this point. For example, what I mean here, let me elaborate. If I have something like this, right? Let us say GSHS has no this uh, uh, initial open loop pole zero map, right? So when I say that some point I am considering in complex plane, let us say this is the point S0. Okay, this is the point S0. Now, for this point to lie on root locus, the magnitude criteria tells us the magnitude of GSHS should be equal to what? 1 here. So how do we find out magnitude of GSHS at this point? I know S0. S0 will be equal to what? Some value A naught plus J B naught, right? So in simple way, I will substitute the value of S naught, whatever it is, right? A naught plus J B naught, and I will find out the magnitude, right, of this. And if the magnitude is equal to 1, I would say that this point is satisfying magnitude criteria, but that alone is not enough or sufficient for it to what? No, lie on root locus. It has to satisfy angle criteria. Angle criteria means what? Again, I will find out angle of GSHS at this point by substituting S equal to A0 plus JB0 in the given open loop transfer function. And if angle comes out to be an odd multiple of 180 degrees, like 180 or 3 into 180 or 5 into 180, like that, I would say now this point S naught is lying on root locus, right? So normally, how do we find the angle contribution? What we do, instead of doing it with calculator, we will be connecting this point of interest with each of the open loop poles and zeros, right? So I will be connecting, let me draw it again, it has not come out nicely. So let us say this was the case, right? I considered, and somewhere here is the point S naught, right? So I will be connecting this point S naught to each of the open loop, poles and zeros, right? Yeah, let us say this is the point. So I will find out the angle subtended by these poles and zeros at the point of interest S naught. And let us say this angle is theta 1, this angle is theta 2, this angle is what? Theta 3. Then in this case, what will be angle GSHS? Yes, at S naught, at S equal to S naught. We know poles, they lie in denominator. This cross or multiplication sign indicates what? Poles. Poles lie in denominator. So they will contribute a negative angle, right? Overall in GSHS. So we know that from no polar form of no representation of complex quantity, right? Angle quantities in denominator will contribute a negative angle in the overall function. So it will be minus theta 1 minus theta 2. See how I am measuring angle? I am measuring angle made by each pole at the point of interest with positive real axis, right? In anti-clockwise direction. I will always measure angle in this manner, right? In anti-clockwise direction with respect to positive real axis. So minus theta 1 minus theta 2 minus theta 3, right? Let us say uh, somewhere here I have a 0 also, right? Where should I put my 0? Let me put a 0 here. Okay, there is a 0 also. And this is the angle contributed by 0, theta 4. So for adding that angle, I will just put plus theta 4. Remember, zeros are in numerator of transfer function. So they will be contributing what? Positive angle. So in this way, if sum of this angle is a multiple of what? Odd multiple of 180 degree, then we say they are satisfying the angle criteria. And How do we find out the magnitude criteria? One is simple, by putting S equal to S naught in GSHS, right? You must be no, watching that I am always talking of GSHS. Remember, GSHS is open loop system, but the criteria which we are using, if satisfied, will give us what? Roots of closed loop system, right? Roots of characteristic equation of closed loop system, something very important. From open loop transfer function, we are determining possible roots of the closed loop system. That's what the power of the technique. And the technique has come from this simple uh, realignment of the mathematical equation. The characteristic equation is 1 plus GSHS equal to 0. So if you realign these quantities, then GSHS becomes equal to -1. And now events from here onwards made these two no, conditions. One is magnitude condition, another is what? Angle condition. And that later on became such a powerful no, method of graphically obtaining the root locus, constructing root locus of all possible values of the roots of closed loop system. So remember, this was one important step that he did. From this characteristic equation, he thought if roots that satisfy, if the points that satisfy this equation 1 plus GSHS equal to 0 have also to satisfy GSHS equal to -1, right? Because this equation is only this equation, right? Rearranged. And then for that case, he had these two conditions, magnitude condition and angle condition. Something very important that you need to underline, right? Understand. Now, where we were, yeah. How we will find out magnitude criteria? One is by simply putting S equal to S naught in open loop transfer function and evaluating its modulus, which we know how to do it for complex quantities. Or another way is obtaining the phasor lengths. If I have this phasors, let me say this is length P1, or if it's not very clear, let me redraw here. If, or let me clean some space here first. Yeah. So here, if I look at it, so if I have V1 GSHS something like this, right, with 3 poles. Okay. Now let me have a 0 also here, right? Just let us say we have some GSHS of which pole 0 mapping is like this, and I am talking of this particular point as not, whether it would lie on root locus or not. So I will be joining that point of interest with each of the open loop pole and 0, right? This is how I will join this point S naught with all the open loop poles and 0, 3 open loop poles and 1 open loop 0. Then this phasor length, this is P1. Phasor lengths mean the line that is joining each open loop pole and 0 to point of interest S naught. This phasor length is P2. This phasor length is P3, and this phasor length is P4. Then for magnitude of GS HS, right, at S equal to S naught, I will get something like this, right? What will be the magnitude contribution here? It will be product of what? The phasor lengths, right? Sum of the phasor lengths. 1 minute. Yes, the product of phasor lengths of zeros to product of phasor lengths of poles, right? That should be what? Unity. That should be what? 1. Right? That is what the magnitude criteria tells us. Like it should be something upon P4 upon P1 into P2 into P3, right? So this will turn out to be what? 1, simply. This also we can do graphically, right? or otherwise s equal to s naught, we have to substitute in what, g of s into h of s. Sorry, this is what we know have the two criteria, magnitude criteria and the angle criteria, that allows us to know if a point in the S plane, right, falls on the root locus or not. Because all points that satisfies 1 plus GSHS equal to 0 will also satisfy GSHS equal to -1. And these points which satisfies this condition are nothing but the roots of characteristic equation, right? So we use these two criteria to determine existence of point on root locus or not. So that's what it is. We just a minute, we take it further now. Let us look formally now into the rules, set of rules which are developed by events in helping us to construct the root locus for a given control system with help of its open loop transfer function. Now, rule 1 states that the root locus is symmetrical about the real axis. This we can very well understand why he is stating so, because roots normally they lie on what, real axis, and if at all they lie on if they are complex, then we know they always have the accompanied conjugate, right? If this is the complex root S1, then it will have its pair S2, right? Conjugate pair, because complex roots can't exist in isolation. They are always accompanied by a conjugate root. So complex roots are what? Having conjugate pairs. So naturally, then root locus will also be what? Symmetric. Since these two roots are symmetric about your real axis, you can see. So the root locus that will eventually develop will also be what? Symmetrical about the real axis, right? Let me move it here. Yeah. So that is rule 1, that tells the root locus will be symmetrical about the real axis. And second rule now tells us is about the branches that root locus will have, right? No, for a given closed loop system. Now, this tells us that the number of root locus branches will be equal to number of open loop poles. It is telling us that root as k increases from 0 to infinity, each branch of root locus originates at open loop pole with k equal to 0 and terminates at either an open loop 0 or infinity with k equal to infinity. Right? We will see that it's how it has come to be like this. The number of branches of root locus will be always equal to number of open loop poles. The rule 2, if we uh, understand, tells us the number of branches of root locus will be equal to number of open loop poles, and the root locus branch originates at open loop pole for k equal to 0, right? So let us understand this much first, what it means, that the branches originate at what, open loop pole with k equal to 0. Then we go to rest of the thing. Now we know in general this is what a characteristic equation is given to us, right? 1 plus GSHS equal to what? 0. 1 plus GSHS equal to 0 is the characteristic equation. And if I write GSHS in factored form, right, then the poles will be given by the product of all these zi's. If there are m number of poles, so there will be m such factors, right, in numerator. And poles are given by the product of all these factors. And if there are n number of poles, there will be n such factors, right? So that is how we write. Or in normal way, this is what GSHS in no pole 0 representation is given. It will be written as what? S plus 1, right? S plus 2. If these are the zeros of the GSHS, open loop transfer function. And let us say these are what the poles S plus, let us say 3, and let us say there is one pole at origin and S plus what 6. Okay. So we know that this form of representation is a pole zero form of representation, where in each factor coefficient of S is unity, right? And the right hand side in each factor, right hand side of plus sign gives us what the poles and zeros. So for this, what will be poles and zeros? Poles will be one at origin, one at what -3, and one at what -6. And what will be zeros? One zero will be at -1. By O symbol we represent zero, and 10 will be at what -2. Right? That is what it means. So if I have transfer function GSHS in no whole zero representation, then I can write them like this: product of all these factors. Pi symbol indicates what? This pi symbol indicates product of product, right? Of. So this is how we depict a open loop transfer function GSHS, right? This is GSHS. This quantity is what? What is this quantity that I have encircled? GSHS, right? So if I have something like this, 1 plus GSHS, right? Characteristic equation right hand side will be what? 0. So I got 1 plus GSHS equal to 0, and GSHS is represented in pole 0 form with K kept outside, because this is the quantity which we will be varying, right, over 0 to infinity to find out corresponding roots of the characteristic equation of closed loop system. Now, in this equation, I just do little reorganization, and I end up with this bullet point, right? When I multiply, take as this product term to multiply it with unity, right? And here it will become 0. So I end up with this second, this bullet point, right? The last bullet point. This is also the characteristic equation, right? Now, in this form of characteristic equation, when I put k equal to 0, right? When I put k equal to 0, then what will be this becoming? On k equal to 0, it will become product, that is no that is pi for j equal to 1 to n s plus pj plus 0, right? Anything into 0 will be 0, so I need not worry about that. So this remains only how much then? Product of s plus pj, right? J running from 1 to n, j running from 1 to n equal to what? 0, right? Plus 0. So that is 0. So this is equal to 0. Or what is the solution of this equation? Solution of this equation will be what? Minus pj, right? Where j runs from what? 1 to what? N. And what are these minus pj? They are nothing but open loop poles, right? So when k is equal to 0, when k here is equal to 0, the solution of this equation is nothing but open loop poles, which we see here, right? We are getting s as equal to what? Minus pj. And if there are 4 open loop poles, you will get no 4 roots of the characteristic equation for k equal to 0. That means when k is equal to 0, the roots of characteristic equation of closed loop system fall on open loop poles. So this actually is right. For this example, if we keep this example in mind, then this symbol cross, which is a open loop pole, actually now is acting or has become a open loop, has become a closed loop pole. Roots of closed loop system are closed loop pole. For what value of k? For k equal to 0, right? For k equal to 0, these open loop poles have become what? Roots of the characteristic equation of closed loop system, which are closed loop poles. And how many are such number of closed loop poles or roots of characteristic equation? 3 in number, and that is equal to open loop poles. So that is first thing we need to understand from rule 2. The number of branches of root locus will be equal to number of open loop poles, and each branch originates at open loop pole, right? What are these now? These are the closed loop poles. So each branch of root locus originates at open loop pole, right? And when is this valid? When k is equal to 0. So for k equal to 0, each branch of root locus starts at a open loop pole. Remember, right? This is what the relation we have understood here. And now, as k tends to infinity, what happens? Now, when k tends to infinity, let us see the no, change in the value of the roots of the characteristic equation. Let me clean it here. So now when we are talking of k becoming infinity, right? Now what I do, I again do a simple mathematical trick. I multiply now to this equation, right, which we have earlier seen, right here, this equation. If I take k on this side, it will become what? 1 by k, right? So the equation, same equation results here. I have now 1 by k multiplied to product term of poles plus product term of zeros equal to 0, right? Or simply I am multiplying 1 by k to the entire equation, right? So I get this new equation. Now here, if I put k equal to what? Infinity, then what I see, right? Always remember, this is still what? Your characteristic equation. So solution of characteristic equation gives us the roots of characteristic equation, which are called as closed loop poles, right? Now, when k is equal to infinity, this term of the characteristic equation, right? This term of the characteristic equation that I have encircled will become what? 0, because 1 by infinity is 0. 0 into anything is what? 0. Then what is characteristic equation left with? It is only left with second no product terms, that is product of s plus zi equal to 0 when I runs from 1 to m. M is number of open loop zeros here, remember. Now this is the no left out characteristic equation for the condition when k is tending to infinity. And solution of this equation will be the roots of characteristic equation. And what are the roots of characteristic equation here when k is infinity? Minus all minus zi's, where I is running from 1 to m, right? So the roots of characteristic equation have become what? The open loop zeros of the transfer function, remember, right? So we say that in rule number 2, if you see in rule number 2, we say that just 1 minute. The branch originates at open loop pole with k equal to 0 and terminates at what? Open loop 0 with k equal to infinity. First understand this. Here it is terminate at open loop 0 or on infinity also. We'll come to that later. But first let us understand what it means here, that it terminates at open loop 0 with k equal to infinity, which is something we just saw here before our eyes, right? So this uh, characteristic equation for k becoming infinity is reduced to this here, right, where my cursor is moving. And this solution is nothing but what? Open loop zeros. So the roots have become what? Open loop zeros. So all the branches that have started at open loop poles with k equal to 0 have now ended up terminated at what? Open loop zeros with k equal to what? Infinity. So this is what we have to understand here, right? See, the branches which started at open loop poles with k equal to 0 for root locus, right? Some of those branches will terminate at open loop zeros because for k equal to infinity, the roots of characteristic equation end up becoming open loop zeros. That is what the point you have to understand. We further continue our discussion in next class. Let us stop here.